Alright, so this is Unit 10, um, Lesson number 2, and we're going to go through and show you how to identify a reaction that's a redox reaction, which means that not all reactions are redox reactions. If you remember, we went through in one of the units, I think it was Unit 5, when we balanced chemical equations, one of the things we learned was how to identify different types of reactions. There's synthesis, decomposition, single replacement, double replacement, and combustion reactions. And out of those five, four of them generally are redox reactions. For the most part, double replacement reactions are generally not redox reactions, and we'll go through and explain what that means. The only way to, if you don't know that, the only way to identify a reaction as being redox is you have to do what we just did at the end of lesson number 1. If you're given a reaction, whether it's single, double replacement, etc., you have to find the oxidation numbers of the elements on both sides of the equation, and then look at them and compare from one side to the other, one element on one side to on the other side, and see if the oxidation numbers have changed. If they have, chances are it's a redox reaction. If they haven't, then it's not a redox reaction. A couple of things, and this is something you have to be careful of, and this is something, again, you already know, that oxidation numbers, not all oxidation numbers, but oxidation numbers in general are listed on the periodic table. You'll see that, for example, carbon has 3 oxidation numbers. The first one is the most common one. It doesn't mean that that's going to be the one that you're going to use every single time, but it is the most common one. Also, you need to remember is that not all oxidation numbers are written here. These are the most common ones. So if you determine that an element's oxidation number is, let's say, a +3, and it's not listed on the periodic table, doesn't mean that it doesn't exist. Okay, so let's go through, for example, these three things. Single replacement reactions, we already know, we talked about this, are synthesis reactions. But if somebody said to you, somebody gave you this equation and said, is this a single replacement reaction? Is this a redox reaction? Well, if it's a single replacement reaction, that means the zinc is higher up on table J, so it's going to react and it will kick the hydrogen out, and you're going to be left with zinc chloride and H2. Remember, H, when it's by itself, is diatomic. It's one of the Brinkelhoffs. You also need to understand why is it ZnCl2 and not just ZnCl. Well, remember, zinc is a +2 charge. It thinks it's in group 2. When chlorine's in a binary compound, meaning only 2 elements, it's a -1. Okay? So the oxidation number here is +2 for zinc and a -1. So let's take a look. What happened? And hydrogen's 0 because it's by itself. Well, the zinc goes from 0 to a +2. That's an increase in oxidation number. That's oxidized. That means that the zinc with a 0 was oxidized. The hydrogen went from a +1 to a 0. It went down, so that's reduction. Notice that the chlorine didn't change, and that's called a spectator ion. Spectator ion. Not a definition that you need to know, but you need to be able to identify a spectator ion in a chemical equation. Let's see. Let's go on to the next one. I'm not going to worry about the stuff at the bottom. Let's do double replacement reactions. Now, double replacement reactions always start out with 2 compounds, and what's going to happen is the first element in each will switch. So the Na will switch with the H. So the Na will join with the Cl, and we know sodium chloride is NaCl, and then you're going to form water. And it's already given you the oxidation numbers here. It didn't do, now the problem you have here is that OH, they gave you the oxidation number for the OH together, but we know that oxygen's a -2 and hydrogen's a +1, so we're going to do that. Sodium is in group 1, it's a +1, chlorine's a -1, hydrogen's a +1, oxygen's a -2. So let's go through and say, well, the sodium started out as a +1, it stayed a +1. That's interesting. Let's do the oxygen. The oxygen here is a -2. Oh, it's a -2 on this side. The hydrogen's a +1 here, and it's a +1 here. So this is not a redox reaction because there was no oxidation and reduction. None of the elements changed their oxidation number. Okay? Now, there are, and I'm not going to go through every single one of these, but there are rules that you need to remember, and you should know most of these already, that will help you to determine the oxidation numbers. And this is something we already talked about. If you have an element that's by itself, meaning it is uncombined, it's not in a compound, it's going to be 0. Doesn't matter if it's a metal or a non-metal. You just have to worry about the Brinkelhoffs. Because if you have one of these by itself, it's always going to be in a pair. Right? If you want to put 2's for all of these. Even though there's 2 of them, if they're not in a compound, it's always going to be 0. Right? Because a compound would have to be 2 different elements. So these would all be zeros. Another thing that we talked about was that in compounds, the charges, the pluses and minuses, have to add up to 0. And you might say, well, wait a minute, how does this add up to 0? Well, magnesium is a, well, I guess I can do this. Magnesium's a plus 2. If you look on the periodic table, 3 times plus 2 is plus 6. And nitrogen is a minus 3. 2 times minus 3 is minus 6. So they do, the plus 6 and the minus 6 do add up to 0. Okay, let's move on to the other rules. Alright, so here's one thing we talked about. When you have a compound that's a polyatomic ion, in other words, let's do this one here. We forgot to do this one. Might as well do this one. Hydrogen's plus 1. There are some that you know all the time. Oxygen's a minus 2. Now you might say, well, wait a minute. We use the minus 3 here for nitrogen. Is it minus 3 here? It might be. But the fact that we use minus 3 is only in a binary compound. If you have a ternary compound, really all bets are off, except for hydrogen and oxygen. They're always going to be a plus 1 and a minus 2. So that's 3 times 2 is negative 6 for the oxygen. We have 1 hydrogen is plus 1. So we know the nitrogen has to be, in this case, a plus 5. Notice it's not even a 3. It's not even a negative 3. It's a positive 5. So those are, excuse me, the oxidation numbers, plus 1, plus 5, and minus 2. Okay. Next is, what about if you have an element who